Hey class, Adam Ward here. I want to talk you through the three-point problem in hydrogeology. This is not just something that's used for groundwater surfaces. Folks also use this if they're interested in getting at things like the strike and dip of geologic units. But for our purposes, we're going to apply it here to understanding which way groundwater might be flowing. So a three-point problem is classically asking the question, which direction is something tilting? So it's allowing us to find the steepest gradient for a planar surface. And we need 3 points to do that. So the slang for this is three-point problem. It's the reason that wells typically get installed in ways that we can evaluate these gradients. So how would a three-point problem work? Let's imagine for a moment that we've got these 3 wells that are installed. And in each of them, I'm reporting the head, total head, so the water surface elevation that would be measured in the wells. So step number 1 is going to be to connect the highest and lowest points with a line. So we're connecting 20 to 16 meters there. After that, we'll take that intermediate value, in this case 18 meters, because that's what is at the 3rd well. And we're going to find where that is on the line we had just drawn. So you can see I've made this quite easy because the midpoint of that line is where we're looking for. So we're finding that head by interpolating along the blue line. And we're going to connect that, drawing a dashed orange line here. And that orange line then represents an equipotential line. So every point along that dashed orange line, the head is believed to be 18 meters. We can draw parallel lines of equipotential. I'll draw a few here. You don't have to do these through the other 2 wells. I'm just choosing to because it makes it a little more clear. So we're drawing lines parallel to that equipotential line. So we're assuming that the water surface here has a linear slope to it, or it's planar. It's not curved. That's a reasonable assumption in most cases, particularly over relatively small areas. Now, from there, we're going to draw a flow line. And so the direction water would be flowing should be perpendicular to the equipotential lines. So we can pick any arbitrary point that we like to draw this flow line. But the idea is that the black line, flow line that I've drawn, is perpendicular to all of the equipotentials. Now, to get at the gradient, we're going to pick out a section of that line. It's convenient for you to do that between 2 of the equipotentials that you've drawn. So you can see I drew this red arrow between the 20 and 18 meter equipotentials. We can get the change in head along that line. In fact, it's quite straightforward. We know the top green line there is 20 and the orange line is 18. So along that red line, there would be 2 meters of head, 2 meters of head loss, I should say, or head drop. And then we can get the length of that line because we're given a scale in the map view or plan view here. So that little scale bar that I've highlighted that says 100 meters, I'm using that to estimate my red lines are about 150 meters. And of course, if you're working this out on a sheet of paper with a ruler, you can be much more exact. So you've got DHDL, you've got a direction here. Where do we go from there? Some common extensions are actually describing which direction this is. So you can construct some triangles and use right triangle geometry to calculate angles. What is the angle from north, for example? Where is the angle from vertical? You could also then use this DHDL and the given information about hydraulic conductivity and porosity to make estimates of discharge, specific discharge, velocity, and so forth. So the three-point problem is really about getting you at 2 key pieces of information. 1 is the direction of water flow, and 2 is the hydraulic gradient. So this is how we take data from wells in the field, even though they might not be organized along our gradient, but they give us information that lets us discern or otherwise back out what that gradient is and what that direction of flow is. All right, that's the three-point problem in 1 slide. Thanks, class.